Welcome to this explainer. Today, we're diving straight into inside cooling versus outside exhaust, and exactly why your cooling tower must always be bigger than your chiller. It's a fascinating hidden puzzle sitting right on top of almost every major building. Let's get into it. Now, if you buy a 100 capacity indoor cooling machine, why does pairing it with a 100 capacity outdoor exhaust system lead to total, catastrophic failure? I mean, matching a 100 to a 100 seems like perfect common sense, right? You pull 100 units of heat out of a room, you should just need a system that throws 100 units of heat outside. Seems completely logical. But if an engineer actually builds it that way, the whole system is going to overheat, the machines will literally choke, and the building will turn into an absolute oven. So what's going on here? Well, it really comes down to a classic mix-up in how we measure things. On the inside, we're talking about an indoor cooling unit measured in what's called a refrigeration ton. But on the outside, we use an outdoor exhaust unit, known as a cooling tower ton. Sure, they both use the word ton, and yeah, they both measure cooling capacity, but they are completely different beasts. One measures the heat ripped out of your office, and the other measures the heat dumped off the roof. To figure out why matching them breaks everything, we've got to look at what each side is actually doing. Let's start with the refrigeration ton, or RT for short. This is all about the exact amount of heat removed from an indoor space. And the history here is actually pretty cool. Back before modern AC, people literally used massive blocks of ice to keep things cold. So 1 RT was defined as the exact mathematical amount of heat you have to suck out of 1 ton of pure water to freeze it solid in exactly 24 hours. When you buy a 100 RT machine, you're buying the power to freeze 100 tons of water a day. Simple enough, right? It's entirely focused on the heat pulled from the room, nothing more. Okay, but what about the outside? Enter the cooling tower ton, or CRT. This unit is strictly for those massive fans and water towers you see up on the roof. It measures the total combined amount of heat that the outdoor tower must physically throw away into the atmosphere every single hour, just to keep the whole cycle running. Notice that word combined. That's our big clue right there. The CRT tells us the outdoor system is dealing with way more heat than we just pulled from the room. But where is that extra heat actually coming from? And here is the answer to our mystery. The total heat thrown outside isn't just the room heat. As you can see, the biggest chunk is definitely the room heat removed, RT, but check out that second slice, compressor motor heat. You see, to pump that refrigerant around the building, the cooling machine works incredibly hard. That compressor motor uses a massive amount of electricity, and thanks to mechanical friction, it generates its own heat. The act of cooling the building literally creates extra heat. Because of this, the exhaust load pushed up to the roof is actually 30 to 40% larger than the heat we pulled out of the room. If that sounds a little abstract, just think of the sweaty mover effect. Say you want to move some heavy boxes out of your living room. Those boxes represent the heat in your room. You hire a mover, which is your compressor. Now the mover picks up the boxes and carries them out. Great, but lifting heavy boxes is hard work, so the mover starts sweating and radiating their own body heat. By the time they hit the front door, the outside air has to absorb the boxes and the mover's sweat. Your outdoor cooling tower is that front door. It doesn't just exhaust the room's heat, it has to exhaust all that mechanical heat created by the machine doing the heavy lifting. So, knowing all this, how do smart engineers avoid building a total disaster? They use a strict 1.5x safety multiplier. If your building needs 100 tons of indoor cooling, a pro won't even mess around with a 130 or 140 capacity exhaust tower, even if the compressor only adds about 30 to 40% more heat. No way. They intentionally over-engineer the roof and install a 150 capacity tower. That 1.5 multiplier guarantees that even on the absolute hottest day of the summer, when the compressor is working at its absolute maximum, the system has plenty of extra margin to safely dump both the room heat and the machine heat without skipping a beat. But let's be real, relying on old-school historical units like refrigeration tons and trying to remember safety multipliers is pretty clunky for modern engineering. So the industry has a brilliant solution. We're transitioning to universal metric units like kilowatts or kilocalories per hour to completely eliminate these mathematical mix-ups. By mapping out pure physical heat energy in kilowatts, an engineer can just look at a spreadsheet and see it clearly. The room produces 350 kilowatts of heat, the compressor produces 100, so boom, the roof absolutely needs a minimum of 450 kilowatts of exhaust power. No historical confusion, just pure, undeniable physics, perfectly mapped out. Which brings us to a really fascinating final thought. We just learned that the simple act of trying to cool a room inherently generates 30 to 40% more heat that we have to invisibly manage. It kind of upends how you look at the buildings around you, doesn't it? So, I'll leave you with this. How many other invisible inefficiencies and hidden mechanical balancing acts shape the buildings we live, sleep, and work in every single day? The built environment around us is absolutely packed with these engineering secrets. Thanks for joining me for this explainer. I really hope this changes how you think about that AC humming in the background, and definitely keep asking questions about how the world around you really works.